Welcome to our next lesson. It is about solving constant acceleration problems. There's the title there, and there are really two methods you can use here, and we're going to be exploring both of them. One is the formula method, and one would be the graphical method. So in the formula method, you really have to have a choice between are you using constant velocity, and now the only formula that you're really going to be using for constant velocity is v is equal to delta d over delta t. So this velocity here can be the constant velocity, or as sometimes it might look like average velocity. You can also use that. What does that look like? If you have a VT graph, constant velocity would be a horizontal line. It could be horizontal 0 or horizontal positive or horizontal negative. Now constant acceleration, and I guess constant acceleration that's not a zero acceleration, you would use our big 5. So this is the big 5 that you've just been working on. And by the way, if you accidentally used the big 5 when you had a situation for constant velocity, at constant velocity the acceleration is equal to 0. So when you think about it, in this first formula, this part would end up being 0. In the second formula, this part would end up being 0. There would be no change for our third one. This would be 0, and then this one would be 0. And at constant velocity, v1 and v2 are the same. We just, instead of having v1 and v2, we just talk about v here. So you'll notice that this is your constant velocity. Delta d is v times delta t, which is just this same formula here, just rearranged. So just kind of an interesting discussion is that you could accidentally use the big 5, and it would still work out just fine. In our first formula, I'll note, just for a little method for picking them, this is the one that does not have v2. Our second formula is the one that does not have v1. This one does not have acceleration. This one does not have delta d, and this one does not have delta t. It wouldn't be a bad idea to have that on your formula sheet, and I would allow you to use it for quizzes just to help you pick things out. So now when we're talking about the graphical method, the number one graph you're going to be using, in fact this is really the only graph you're going to be using throughout, is going to be your VT graph. So the two things to remember, and how many times have we talked about them? The slope of the VT graph is acceleration, and the area under the line for a VT graph is displacement. Let me just talk about one type of an example. If we throw a ball in the air, so if I take a ball and I throw it so it has that kind of a path and it's going to hit the ground, at the very beginning it would have a very large positive velocity, and as it goes up it would have a smaller and smaller positive velocity. If I'm just talking about the velocity up or down and not horizontal, at the top it would have a zero velocity. It would just stop for an instant, and on the way down it would be speeding up. So if I was to make a VT graph of this, it actually starts up here because it starts with a very large positive velocity. This would be the highest point, right? So this spot here corresponds to this spot here, and then it would come down. The slope of this line would be the acceleration. So the slope, if we're doing this close to the Earth, would be equal to negative 9.8 meters per second squared. And remember about the area under the line being displacement. This area here, this is above the line. This would be positive displacement, and this one over here would be negative displacement. So if I drew this correctly, then this positive and this negative, perhaps my delta d would end up being 0, and that just means that I threw it, it came up and then it came back down to the same spot. Okay, so let's take a look. I'm looking at the length of this video, and it may just get chunked into two smaller ones, and you might want to spread it out a little bit. So the question says, why is the VT graph most useful? Because if you've got the VT graph, the slope gives you acceleration, and the area under the line gives you displacement. So you can get all three of our big kinematic kind of concepts through the VT graph. The first question says, a car is traveling 45 kilometers per hour when it begins to brake, taking 4 seconds to come to a complete stop. Well, the first thing I'm going to do is I'm going to recognize that we would like to have this 45 kilometers per hour change to meters per second. So 45 kilometers per hour. I won't go into the the y, but this is a good one to remember. If we simply divide by 3.6, and then I believe we get 12.5 meters per second. Might not be a bad idea just to stroke that out here and then write 12.5 meters per second. Okay, so now it says find the car's negative acceleration and find the car's displacement. So we're going to do two methods here. First method we're going to do is the formula type method, and then over here we'll do graphical. Hopefully we'll have enough space to do both of them. So in the formula style method, well, is it constant velocity or is it changing velocity? Is there some acceleration going on? In fact, even though we're going to do the formula first, just to get a sense of what's going on, sometimes I like to make a VT graph anyways. It starts at 12.5, and then 4 seconds later, okay, so this is my origin, here's my 0. So the velocity is in meters per second, and the time is in seconds. This is a fancy enough graph. We were just sketching it real quick. This is going to look like that. Okay, so if we're going to do the formula method, let's write out all the stuff that we know. And V1, V2, A equals, delta D equals, delta T equals, there's those 5 things. So what do we know? The initial velocity was 12.5. The final velocity was 0. The acceleration, that's what we want to know in the first question, so I'll put a question mark there. The displacement, that's what we're going to want to know afterwards, so I won't put a question mark yet, but when we get to part B, I'll put a question mark there. And the time is 4. So the first thing we want to do is we want to use one of the big 5, the one that does not have displacement in it. So if I go back to my list over here, the one that does not have displacement is this equation number 4. V2 equals V1 plus A delta T. So if I write that out here, I'll get V2 equals V1 plus A delta T. And now I'll substitute all the things that I know. 0 is equal to 12.5 plus A times 4. Now being very careful with my algebra, first I'll subtract 12.5 from both sides. And then I'll divide both sides by 4. And then I find out that A is equal to 3.125, and negative meters per second squared. Okay, so I got the first part done, and that's a negative. The second part, see if I can squeeze some room in here somewhere, is to find the car's displacement. Okay, so if I sort of make some room over here, there, I'll squeeze it in over there, and I'll try green so that it works. Okay, to find now the displacement, now I'll put a question mark over here, and now we can use any of our big 5 as long as it does have displacement in it. Perhaps we'll take the one that does not have acceleration, so in case we made a mistake in our first question. So the one that does not have acceleration is this one here, is equation number 3. So we'll take that one there. We'll say delta D equals V1 plus V2 divided by delta T, and if we plug in all the things we know here, we get 12.5 plus 0 divided by 4, and so our answer I think works out to 25 meters. Okay, kind of like a grade 11 style way of doing those questions. Now let's go over and try to solve this graphically. So the first thing we want to do is A is find out the acceleration. Well, on a VT graph, the acceleration is equal to slope. So I'm going to say A equals the slope, which is the same thing as the rise over the run, which is equal to, now how much does it rise? It actually goes downward, so it rises minus 12.5 divided by 4. And here we get our same answer of negative 3.125 meters per second squared. If you're not sure about the units, the rise velocity was in meters per second divided by seconds, and that's how you get meters per second squared. Part B is now we have to find the displacement. So the displacement, delta D, is equal to the area, which is 1/2, just a second, times the base times the height, because it is a triangle, so it'll be 1/2. I'll put the units this time. The base here would be 4 seconds, for s for 4 seconds, and then the height would be 12.5 meters per second. So when I multiply that out, a half times 4 is 2, 2 times 12.5 is 25. The seconds multiplied by the meters per second, the seconds are going to cancel out because there's 1 in the numerator, 1 in the denominator. So we get 25 meters. Now isn't that cool? We got the same answer regardless of which way that we solved it. I will probably have a question where I'll say solve this question graphically, or I may say solve this question using the formula. I want you now to do a your turn. So I would like you to try this question on your own. So what I'd like you to do is press pause, try the question, and then come on back. Alright, now instead of me slowly solving the problem, what I'll do is I'll press pause myself and solve it for you, and then it'll all show up. And ta-da, here's your answer. So I've made a nice little VT graph of it first. I used my formula method, and I got an answer of one just like the answers that were given. It's pretty straightforward, very, very similar to the last example. Let's take a look at example number 2. This gets a little bit more complicated. Here we have a car that first of all accelerates at a constant rate from a rest at the rate of 2 meters per second squared for 6 seconds. Then it goes at a constant velocity, and then the brakes are applied. So I think what we want to do is make a graph, a VT graph, just to get a sense of exactly what's going on here. So this will be my velocity, this will be my time. So it starts from rest, so here's at 0. And then it is accelerating at some 2, so this slope is 2, and this is at 6 seconds here. So we don't know yet what this value is, but we know that this slope equals 2. And then it goes at a constant velocity for 30 seconds. So it seems to me then at this point it should be 6 plus 30 at the 36 second mark. Finally, the brakes are applied and the vehicle slows down at a uniform rate and comes to rest in 5 seconds. So I guess this would be at 41, and it comes down and goes, well, okay, I missed it, but they're at 41. Okay, so for this question here, I'm going to be doing a graphical solution, and then I'll just talk about the formula one because I want to keep it a little bit shorter. So for the graphical solution, I guess the first part is what's the maximum value of the car? So in other words, what's this velocity right there? So let's think about that little piece at the beginning. So we have to kind of do this in separate chunks, and this first chunk is constant acceleration, then is constant velocity, then is constant acceleration again, because here the VT graph is changing, here it's constant, here it's changing again. So let's just consider this first. I'll put a 1 here and a 2 there, so that's like my beginning and the end of the segment that I'm considering. Just from there, we can think about that the acceleration is equal to the slope, right? And that's equal to rise over run. And so if the acceleration in this case was 2, so I can say 2 meters per second squared is equal to, now how much does it rise? This rise piece here, that is going to be the change in velocity. So I'm going to say delta V divided by the run, which is 6 seconds. By the way, this acceleration is equal to rise over run is basically the definition of acceleration. It's how much the velocity changes divided by how much the time changes. This is our definition of velocity, and it's the exact same thing as rise over run on this graph. Pretty clearly here we can solve for delta V. Delta V is equal to 2 times 6, which is 12, meters per second squared divided by seconds, so one of those seconds in the denominator disappears, and I get 12 meters per second. Now because it started at 0 and it changed by plus 12, it must have ended at 12. So I'm going to say this answer for A is that the maximum velocity is 12 meters per second. Notice if the car would have started at some other number besides 0, we would have taken that number, add 12 to it, and find our answer. So I'll add, or I'll just change this part here and say we're putting a 12 in there because we know it now. All right, now the second part of our question, B, is the total displacement. So again, the displacement here is the area. So there's a few ways that we can do the area. We could do the area by chopping this into a triangle, a rectangle, and then a triangle. But hey, just because we know how to do these things, let's look at this and say it's a trapezoid, and let's use our concept of how a trapezoid works. So just a reminder, a trapezoid is the average of the two bases. So here's B1, here's B2, and then there's the height. So the area is equal to the average of the bases, B1 plus B2 divided by 2 times the height. So what are our two bases? One is 41, and the other one is, careful, it's not 36, it's 30, divided by 2 times my height, which is 12. And when I do all that math, I believe I get 426 meters. Now, had I done this using the formula method, I would be solving for delta D. I would say here is my initial segment, and that would be like my beginning and my end, and I would use the big 5. And then I would say this one, and I would use constant velocity. So I would basically say delta D is equal to V times delta T. And then for my last one, I would, instead of thinking this is the beginning and this is the end of my segment, I would switch things around and say, here, if I can erase that and erase this, I would say, oops, say that's my beginning and that's my end now, and I would find out that last delta D. So I would be using probably having V1 and V2, and I would probably using equation number 4 here, and then the definition for constant velocity, and then equation number 4 again, and then add them all together. So you can see that the area part is actually easier for a lot of these questions. Okay, one more, your turn, and then I think maybe I'll close this video and go on to example number 3 in my next video. So again, I'd like you to hit pause and try this one on your own. And I would recommend you to do this one just graphically and save yourself a little bit of time. Alright, so here's the answer that I figured out, or I guess the answers were given. Here's a solution for it. And just once again, here I solved for delta V is 60 meters per second, and because the initial velocity was 0, 0 plus 60 is 60. So it's a bit of a coincidence that these two are exactly the same. It's only because this started at 60. You'll probably see some other questions where it's slightly different. And I will end this video now, and you can start the next one to do example 3.